Hello everyone. Today I'm going to present the proposed precise framework, which is short for Privacy Preserving Cloud-Assisted Quality Improvement Service in Healthcare. My project mentor is Dr. Feng. My name is Chen. I'm a PhD candidate from University of Oklahoma. This is joint work with Dr. Norman Mohammed and Dr. Xiaoqian Jiang. Here is the outline of today's presentation. Suppose a few neighboring hospitals in a county want to aggregate their local private medical data to perform some meaningful scientific discovery to improve the healthcare. However, due to the privacy concerns of institutional regulation, hospitals may not be able to exchange data with others. Existing data dissemination methods such as differential privacy protect sensitive medical data by introducing noises on the raw data, but it is also degrade data utility. In contrast, the proposed framework tries to preserve the accuracy of results without introducing additional noises, and we resort to the combination of side encryption methods to achieve this goal. The proposed framework is mainly based on two basic cryptographic primitives as shown in this slide. They are homomorphic encryption and double circuit. I will walk you through the detail of each primitive in the next few slides. Before introducing homomorphic encryption, let's first take a look at the traditional encryption method, where the data privacy is protected by data encryption during the storage or transferring phases. However, for any further data analysis, one must first decrypt the data. To apply certain operation over the decrypted data, we need to apply certain operation over the decrypted data. Then, finally, one can obtain the answer. The major privacy risk in the traditional method comes from the requirement of decryption before performing any additional operations. In contrast, in the homomorphic encryption framework, one can perform certain operations directly over the encrypted data. And the decryption operation is only required when one wants to obtain the final result. Therefore, we can minimize data privacy risk during all life cycle of data processing. Despite this advantage of homomorphic encryption, it is worth mentioning that homomorphic encryption only supports limited operations such as addition or multiplication with a high complexity overhead. Now, let's introduce the other cryptographic primitive, the double circuit. First, let's introduce a traditional circuit as shown in this slide, which can evaluate the function fxy by taking one input x from Alice and another input from y from Bob. However, the privacy of input cannot be guaranteed in this circuit due to the lack of protection. Then, its counterpart, the double circuit, can evaluate the same function, but by taking doubled input with doubled output, where only authorized user can decrypt the doubled output. Therefore, we can preserve both Alice's and Bob's data privacy, as none of them input the raw data. Let's start with a traditional framework without privacy protection to illustrate the task. Suppose there are M hospitals, where each has its local privacy data, such as the mortality of a subpopulation. Then each hospital may want to rank the mortality among all neighboring hospitals and compare with average mortality in a cloud environment. In case without privacy protection, all the hospitals need to send their raw data to the cloud. That cloud can compare the data and rank for each hospital. Finally, the cloud returns the results. Each hospital gets its mortality rank and the comparison with the average mortality among all hospitals. The hospital may make necessary adjustments to improve the healthcare if it has a higher mortality than that in other hospitals. However, the pre-setup requires the exchange of raw data, which fail to protect data privacy. Next, we will introduce the proposed privacy-preserving framework. In the new framework, we introduce an actual critical service provider, which will cooperate with the cloud to answer the hospital's queries. First, the critical service provider sends a public key to all hospitals and the cloud for homomorphic encryption. Each hospital will use public key to encrypt data and send the encrypted data to the cloud. Because cloud does not have a private key, it learns nothing from the encrypted data. Based on homomorphic addition and multiplication, the cloud can compute the encrypted average over all inputs. By then, the cloud has n+1 encrypted data. In the next step, the cloud generates n+1 random masks. The cloud encrypts all of the random masks using the same public key. Then add each of them with corresponding encryption data following homomorphic addition property. The cloud will get n+1 encrypted summation of the data and the random mask. The cloud will send this encrypted item to the critical service provider. Because the critical service provider has private key, it can decrypt all encrypted items. However, because all decrypted items contain the random mask, the critical service provider cannot learn the actual data. Given the random mask generated by the cloud and the decrypted items with additive mask from the critical service provider, the cloud and the critical service provider can first generate garbled inputs, which can be fed into a garbled circuit for privacy-preserving comparisons. The garbled circuit will subtract the garbled random mask input from the garbled input provided by the critical service provider in a private preserving manner. In other words, all the intermediate results in the garbled circuit are still garbled values. Then, the garbled circuit performs comparison operation over these garbled values data to get hospital ranks and their comparison with average mortality without reviewing any raw data. Finally, the cloud will send the ranks and the comparison to the corresponding hospitals, and the hospital can use this information as reference to improve their healthcare. We extracted 924 SU death record data from MIMIC2 clinical dataset. This table shows the attributes of each record. We evenly split the SU death record among 4 hospitals. This table shows the comparison result under different criteria. For example, the people 13th, 14th, or 15th unmarried persons. For each criteria, our method securely outputs the ranks of each hospital. In this table, the red ranks indicate the corresponding mortality is above the average in the corresponding criteria. This slide shows average execution time of each key cryptographic operations over 1,000 trials. We can see that the garbled circuit is the most time-consuming operation. Moreover, we provided the estimated execution time of the same operation that was applied on the plain text as a reference. This is summary and future directions. We have implemented arithmetic and comparison operations in cryptography method based on cloud client model. In the future, we will build advanced systems such as regression model. We will speed up the computation through parallel computing. This is the paper submission during my internship. Finally, thanks my mentor, collaborators, and thanks all professors, staff, interns, and thanks iDASH, DBMI, and AIH. Thank you.